Hello, in this video we will talk about molecular orbital theory, which is in the first part of chapter 9. And so you've seen this slide before, and my point of including it now is to say that, hey, now we're down here, right? So in Gen Chem we talk about 3 different ways to describe bonds. We have Lewis structures, which are pretty simple, but this is the language of chemistry and we speak this a lot. Valence bond theory is the next level up, where you take hybridized orbitals and jam them together with orbitals on other atoms to make a bond. You overlap them. And now we're going to turn atomic orbitals into entirely new orbitals that span the molecule. And this is called molecular orbital theory. And by way of motivation, okay, Lewis structures, super helpful, but there's shortcomings, and we've talked about lots of shortcomings before. Here's another shortcoming. So if you take liquid oxygen and pour it between the poles of a magnet, so these are the 2 poles of a magnet, the liquid oxygen sticks there. And materials that are paramagnetic will be attracted to magnets. And so what do we mean by paramagnetic? And so this means your atom or molecule has unpaired electrons somewhere. It's kind of a weird word. Paramagnetic, you'd think that would mean paired, but actually that means unpaired. So, and you do need to know this word, so try to keep that straight. Whereas diamagnetic means no unpaired electrons. This one makes sense. There's 2 of all the electrons you have, they're all paired. And now, okay, so if you look at the Lewis structure of oxygen, it looks like all the electrons here are paired. So this doesn't predict that oxygen is paramagnetic, because there's no unpaired electrons, so this should be diamagnetic. All right, then we can go to valence bond theory. So you have your oxygen nuclei here, and you have your sigma bond, you have your pi bond. There's 2 electrons in each. They're all paired. This makes it seem like it should be diamagnetic. But again, experiments show that oxygen is paramagnetic. There's unpaired electrons in here. So obviously we're missing something in our theory of bonding, and molecular orbital theory will get us there. So I think of molecular orbital theory as the closest to the truth that we teach you in Gen Chem, but unfortunately it's also the most complicated. So, all right, we need a truthy theory to describe bonding. How does this actually work? Now, remember when we went and described orbitals in the first place, we used something called the Schrödinger equation, where you basically put in some quantum numbers and out pops the math that describes the probability of finding the electrons in some space. And so then we enclose a 95% probability in a shape and call that an orbital. And so now we're just doing the same thing, except instead of 1 nucleus, we're putting 2 nucleus, some hydrogen nuclei, say, at a fixed distance, and then solving the Schrödinger equation for having 1 electron in there. And this gives us an orbital that stretches across the 2 nuclei. And so this little plot here is showing that as you change the distance between the nuclei, you reach some optimum distance between the 2 nuclei, which has the lowest energy overall. So thus that's the distance between the 2 nuclei when it makes a bond. Okay, so this leads us to molecular orbital theory. We're using the Schrödinger equation, putting in nuclei, and solving for orbitals that stretch across the molecule now. And we can think of these molecular orbitals in terms of atomic orbitals, because you are, in a way, just like valence bond theory, you are mixing and matching orbitals on the atoms, except now we're replacing them to make entirely new orbitals. So that's MO theory. You make new orbitals. Valence bond theory, we were just overlapping them. And I use MO and AO to say molecular orbital and atomic orbital. I can't guarantee you that other people will say AO, but calling it an MO is pretty common. Okay, so what do these orbitals look like? Well, they look like this. One little caveat here, and we did this back when we did the Schrödinger equation in the first place, is that we solved these all for 1 electron. And then we use these shapes to describe what it would look like when we put more electrons in. The reason you have to do this is because solving the math for having 2 electrons gets really complicated. If you have the negative electron on one side of the atom, then the other electron won't want to be right next to it. And so you have to deal with that somehow, and that gets mathematically intractable. So, but we can get the information we want by just solving this for a single before we solved it for a single hydrogen atom, here we're solving it for H₂ plus with only one electron, and we get these shapes, and then we can just use these for everything else we want to do. We also only consider diatomic molecules in Gen Chem just to keep it simple. So, analogous to what we did before, right? Remember when we taught you atomic orbitals, we just gave you a list. Here's the 1s, the 2s, the 2p, the 3s, the 3p, and said, here's the list, memorize it in order. And so we can do that here. Here's your list. It looks something like this. You could just memorize this in order and move on with your day. That's kind of hard to memorize, and we also need to understand why the heck this works. So let's talk about that. All right, so in a way, we're backing up a step to talk about how the orbitals on the previous slide were made. So you can generate molecular orbitals by playing around with atomic orbitals on different atoms. And so again, another key difference here with valence bond theory, the hybridization one, is that we were dealing with atomic orbitals on the same atom before to make these hybrids, and then we just overlapped the hybrids with some other atom. Whereas here we're playing with atomic orbitals on different atoms and adding and subtracting them to make a molecular orbital. And so, okay, if we do this with hydrogen, hydrogen just has 1s orbitals, great. And then you can add them together, you get this nice orbital here. You could subtract them, you get this orbital here. The terminology is pretty similar because in the end we are describing the same thing. This is a sigma molecular orbital, and when you put electrons in here, it will make a sigma bond because the electron density hangs out between the nuclei. And so we call this a bonding molecular orbital. The overall stability here is greater than the individual atomic orbitals when you put electrons in here. Now, the problem is, for the yin, you also have to have the yang. You have to have both sides of the coin. So if you add them, you also need to subtract them, because the total number of orbitals needs to be conserved. So we started with 2 atomic orbitals, so we need to have 1, 2 molecular orbitals. And so when you subtract them, you get this kind of thing, where, well, you have some electron density over here, some electron density over here, and then this big empty space where the electrons don't go in the middle. And so putting electrons here honestly helps drive your nuclei apart. It doesn't hold your nuclei together. And so it's higher energy to do this. And so this is overall lower stability than the atomic orbitals that you came from. We call this an anti-bonding molecular orbital. It's still sigma, but it's an anti-bonding one. And so we'll denote that by putting a little star right here to say anti-bonding with the star. And so you call it sigma, you call it 1s because that's the atomic orbitals from whence it came, right? So sigma that comes from the 1s, the sigma antibonding that comes from the 1s. Further notes about sigma molecular orbitals, they are symmetric around a line that you can draw through the nuclei, and so I make this little thing to say, hey look, it's axially symmetric. And then also, you don't have 1s orbitals anymore, they're replaced by the molecular orbitals. Okay, so remember, we did this stuff where we just added them together and we got kind of a nice blob that connected the nuclei. And then if you subtracted them, well, you got these blobs that didn't really connect the nuclei. And so to make this match what we just said, the nuclei are in here. And then in the molecule, they're kind of in the same spot. And the nuclei are here, and then they're kind of like right here. And so here you're adding together, and here you're subtracting. Now, if you've taken physics before and you know about things like constructive and destructive interference, remember these are waves, and so if you add waves in phase constructively, you'll get this kind of thing. Whereas if you then add them destructively or subtract them from each other, if they're in the same phase, then you'll get some kind of destructive interference. Now, if that made no sense to you, don't worry about it. You could just probably imagine, hey, if you add them together, it works. If you subtract one from another, you get some weird stuff, right? So hopefully this just makes sense intuitively, and you don't need to think about physics. All right, so we did 1s orbitals and the sigma from the 1s, molecular orbitals. Now, as we go up in energy, we have the 2s, and you do the same thing. So now we have sigma from the 2s and sigma star from the 2s. Now, to be fair, while hydrogen itself, that we're actually doing the math on, doesn't have electrons in these orbitals in the ground state, we can still calculate what these would be and then apply these results to bigger molecules. And this is what we did before when we did atomic orbitals. Okay, so that's 2s. Next up in energy is 2p. And so now you get a couple different things that can happen because we have 3 orbitals we're playing with, and then there's a couple different types of geometries. So say you pick the z-axis to be the line that connects the 2 nuclei. So then the 2pz orbitals point towards each other. And we get a pretty similar case to the s orbitals, that we have some good overlap and some bad overlap that's still symmetrical around the line between the nuclei. Okay, to dig into this a little more, something that we may not have told you is that p orbitals technically have different phases in their 2 lobes. And so you can write these as positive phase and negative phase. Sometimes you'll see them colored differently. You'll see this lobe here, this half of the p orbital is one color and the other half is the other color. And that's just how the wave function works out. Oftentimes it doesn't matter because you square this anyways when you're trying to find the probability of finding an electron, so who cares? But when you're adding them together, the sign really does matter, right? If you add them together like this, all right, well then this positive and positive will add together and you'll get a nice range of happy positiveness. And then you'll have some negative out here that doesn't really matter, but it's still out here. And then if you add them like this or subtract one from the other, then the positive here and the negative here, they don't really mesh and you'll cancel out to 0 in the middle. And that's what goes on here. And so this is called a node, which means an area where there is no probability of finding the electron. And so there's a plane that extends in and out of the screen that there's no electron density. A little bit of positive here, a little bit of negative here. But basically, if you put electrons in this, it's not going to help pull the nuclei together. Whereas if you put electrons in here, you got positive nucleus, a positive nucleus. You put some negative electrons in this thing. Even though we call it a positive phase, the electrons are still negative. So you put some negative electrons in this thing, and then it holds the nuclei together. Right? This is a bonding molecular orbital. It's still a sigma molecular orbital, and it comes from the 2p. And the way we set up our coordinate system is we called this z. So sigma from the 2pz. And then you have the same thing with the star on top, which tells you this is the anti-bonding molecular orbital. Again, we took 2 p orbitals, one from each atom, and made molecular orbitals from them. And this helps bond the molecule together, still sigma. They're still symmetrical around a line between the nuclei. Now we can add 2 p orbitals the other way, and we can, do the side-to-side version. And again, you can add them happy. So there's the positive phases are both on top, and then you get your positive phase up here. Negative phase is both on the bottom. You get your negative phase here. This is not a sigma molecular orbital. This is a pi molecular orbital. And this kind of matches our idea of a pi molecular orbital from valence bond theory, where the electrons hang out above and below this line that would connect the 2 nuclei here. But still, if you put electrons in here, it'll help hold the nuclei together. So this is a bonding molecular orbital. It's not as effective as a sigma, but it still does help. Whereas then if you add them together destructively, then you'll get this kind of funky looking thing, where your nuclei are these dots right here, and all of your electron density, your probability of finding this electron, are away from the area in between the 2 nuclei. So putting electrons in here, in this molecular orbital, is not going to help the nuclei stick together. So these are anti-bonding. Down here they're bonding. We call this a pi, bonding molecular orbital. It comes from the 2p, and then you have one version that comes from the 2px, the other version that comes from the 2py. We showed you one of them, and then the other one would be like this except rotated 90 degrees so that, say, this lobe came straight forward towards you, and this part went straight away from you into the page. So just, rotated 90 degrees. Okay, so those are the orbitals we need to know. We got sigma, we got pi. They can come from the s and come from the p. And so here we are. So when you put them all together, you get this kind of thing. Now, the order of these energy levels, we'll get into that in a minute. That's actually kind of critically important, but we got to get there first. All right. So let's summarize the naming we've done so far, right? Sigma and pi orbitals, how to tell what those are. So if you put a line through the 2 nuclei, well, sigma orbitals are axially symmetric around that line. Pi orbitals aren't. Most of the electron density is on that line for sigma orbitals, but not for pi. Sigma molecular orbitals can come from s or p atomic orbitals, whereas the pi molecular orbitals only come from p atomic orbitals. And then bonding means you put electron density between the nuclei, so your little blob goes between the nuclei, and then antibonding means you don't. Okay, time to take a nice mental break. And feel free to pause the video, take a physical break if you want before we carry on. Okay, so one of the things we're going to have you do is draw configurations of these molecular orbitals, and I want to tell you how to do that. And so there's a process for this, and really it's a before and after picture, but it's a little weird that the before are on each side, right? So here's your individual atom before, one of your atoms. Here's your other atom before. And then in the middle, we'll put the after scenario. So now here's the after scenario. And when you have 1s atomic orbitals, the only way they'll combine is to make a sigma molecular orbital. It comes from the 1s, and then you'll have the antibonding one as well. Really, I should have drawn a star and put the star like right here, but that's kind of a pain to do in PowerPoint, so I use an asterisk and park it out over here. Hopefully that's equivalent for you. Okay, now you've got the same number of lines in the middle as you do lines on each side, right? So the number of orbitals is conserved. Now, generally, the more stable the bonding molecular orbital, right? So the y-axis here is energy increasing from bottom to top. And so the fact that the 1s is here and the sigma is lower means that this is more stable to put electrons into this. So however much more stable this is, the other one is less stable. So if you're going to look at that by drawing it, if you were to say, okay, here's my starting value, whatever this distance is here, you have the same distance to the one on top. Right? So however stable this is correspondingly unstable. We wind up violating that, but for now it's a good place to start. All right, another thing we do is we put these little tie lines, I call them, these little dashed lines between the atomic orbitals that we start with and the molecular orbitals that we finish with, just to kind of tie everything together to make it a little easier to see where stuff comes from. All right, now we have molecular orbitals, and then we're going to have electrons in here, and just like before, you fill the electrons bottom to top. So if we're doing, say, hydrogen, each hydrogen has an electron in it, and I don't really care whether you draw this one up or down, whatever. And then when you make the molecule, there's 2 electrons here. 2 electrons can go in an orbital. It's also true for molecular orbitals. And so then we have electrons here, and we don't have electrons in the antibonding orbital, which is good. Now, if you have, say, 2 pi molecular orbitals of the same energy, then Hund's rule is you try to maximize the parallel spins. So that means you put them into each orbital separately, and then you pair them. And then just like orbitals, you need to have the same number of electrons before and after as well. All right, so here we had 2 electrons before and 2 electrons after. So that has to stay the same. Okay, now we can do the same thing for the p orbitals. And all right, you have 3 p orbitals. And remember we talked about how the ones that aim head on into each other will make these sigma orbitals that come from the 2p. And then whatever this distance is, from the kind of midline here down to this sigma 2p, you have that same distance up to the antibonding. Again, we wind up messing with this in a little bit, but when you start out, go for that. All right, and then when you do the pi, well, it's not as far of a distance because you don't get as much of a gain in energy, or as much of an energy reduction, I guess I should say, when you have the electron density outside of the nuclei. Right? So if you've got your 2 nuclei, putting electron density here is better, and that's a sigma, whereas putting electron density out here is not as good, and that's a pi. And so you don't get as much of a savings when you make the pi, so that's why it's not as far down. And then, okay, when you have the antibonding, it's the same distance up. So that's what it looks like when you have the p orbitals. One huge caveat is that these 2 orbitals will often switch positions. And they do this for all homonuclear diatomics. So that means, C2, N2, B2, the random things we wind up drawing. They'll actually switch positions. This sigma molecular orbital, this thing actually winds up here. And then the pi kind of stays in the same spot. So they switch order, if you will. They don't just like swap spots. They switch order of filling. And this is due to something called SP mixing that I'll get to in a minute. I just wanted to put this caveat on here so that if you're taking notes, which you should be, if you're taking notes, you can put an arrow to this and say, hey, this is often not going to be the case. But I'm going to show my first example of something where this is the case. So I'm going to use oxygen, because that's also how we started this whole thing off. So we should, close the cycle here. So let's do the molecular orbital diagram for oxygen. Now, I generally start with the 2s here. Your book will start with the 1s, which is a lot lower, which I don't really agree with, but whatever. So you can start from the 1s, you can start from the 2s, as long as you're consistent and it makes sense. So I'm just showing the valence ones here. So here's the 2s on one oxygen and the 2p on that oxygen. And then over here is the 2s and the 2p on the other oxygen before they bond. And then the molecular orbitals after they bond match what we've been talking about here. So I'm not going to re-describe how these shapes go. All right. So now we got to put the electrons in here. Okay, oxygen has 6 valence electrons. Right, it's atomic number 8, but we're not including the 1s. So we're just doing valence electrons in the way I'm drawing it. So you've got 6 of them. So here's 1 oxygen. 1, 2, 3, 4, 5, 6. That got messy. Here's the other oxygen. 1, 2, 3, 4, 5, 6. All right. So now we've got 6 on each side. So that means we need to park 6 electrons times 2. So 12 electrons into the middle. 1, 2, 3, 4. All right. 5, 6, 7, 8, 9, 10, 11, 12. Huh. That's interesting. We have unpaired electrons right here. Because these electrons are not paired into an individual orbital, that means that oxygen is paramagnetic. And so this brings us back full circle to where we started, which is that oxygen is paramagnetic. And the only way you can describe that is with molecular orbital theory, because these two electrons aren't paired. And now this diagram is the way your book tends to show it, where it just shows the molecular orbitals. Macquarie does this. Just shows the molecular orbitals and doesn't show the whole diagram is kind of a quick way to do it. And again, this is comparable to what we just drew. All right, one other thing that we talk about when we do molecular orbital diagrams is we talk about this idea of bond order, which the simple idea of bond order is that if you got a single bond, the bond order is 1. If you got a double bond, the bond order is 2. If you got a triple bond, the bond order is 3. Well, if you back up to the oxygen molecular orbital diagram, well, it gets a little weird trying to think about bond order when you have all these different MOs. And so we have a formula for that. And basically the bond order is half the number of electrons in bonding molecular orbitals without the stars, minus electrons in anti-bonding molecular orbitals. So this makes sense. If you put as many electrons into the beneficial bonding ones as you put into the not beneficial anti-bonding ones, you're not going to make a molecule, your bond order will be 0. And, right, like a single bond has 2 electrons in that bond, and we call it bond order of 1, so that's what the 1/2 is for, because you'll have 2 electrons in the bond, but then we call the bond order 1. All right, something that's critically important is that the higher the bond order you have, the stronger that bond is, right? So a triple bond is really strong, and the shorter that bond is. So a triple bond is really short. So that's something you definitely need to know, because we'll ask you that on various exams, because it's a nice, simple question for us to ask. Okay, one last thing we have to include in the video about all the molecular orbital content is this idea of SP mixing. Right, when I showed you the p diagram for making molecular orbitals out of p orbitals, I said that the bottom 2 might switch orders, and this is the reason why. So this idea of mixing is more commonly used in quantum mechanics, so it's not just this one thing, but you haven't heard it before, and so we'll talk about it. And so the idea here is when you have things that are at kind of similar energy levels, they will blend together quantum mechanically, and you'll have some character of each other in them. And so here you have the sigma molecular orbitals from the 2s and from the 2p. These are pretty close in energy. And so this will mean that your pi molecular orbital takes on some character of the s, and vice versa. And so this winds up changing the energies of the molecular orbitals. This is not the reason why, but it's a good memory trick, that you can think of these two molecular orbitals occupy the same space, and therefore they kind of repel each other and push each other out of the way. Again, that's not why it actually works, but maybe that's a good memory trick. And so the outcome of this is that you would expect what we have on the left, and then for most nuclei you get what's actually on the right. So let me explain what's on the left. Right, on the left it's nice and symmetrical. When you have the sigma from the 2p and the antibonding sigma from the 2p, right, they're kind of equally spaced around where you started. And then the pi is a little less beneficial, so they're closer in to where you started, but they're still symmetrical. And so now what happens is this sigma from the 2p, it moves above the pi, and so now it's sitting right here. I put it in red. And then the antibonding sigma 2s kind of gets pushed down a little bit. So these two move when you're dealing with mixing. And I encourage you to read the textbook and their description of mixing. Macquarie is a famous physical chemist and does a lot of stuff with quantum mechanics, and so he'll have a really good explanation of it. So I highly suggest that you read that. The ultimate outcome is that whenever you're dealing with homonuclear diatomic molecules that are not oxygen and fluorine, you do this. And it changes the order, and that's what matters. When you have oxygen and fluorine, you'll get the kind of order you might have expected in the first place. Ultimately, it's a little more gradual of a transition than that, right? The sigma is above for boron, carbon, nitrogen, and then below for oxygen and fluorine. It has this kind of nice little trend that as you go to a higher nuclear charge, it shrinks the orbitals in closer to the nuclei, which then makes less of a repulsion, if you're going to use the memory trick. All right. But ultimately, we care about order and filling of electrons, and so the dividing line here makes a lot of sense for us. Do you put electrons in the sigma first, or do you put them in the pi first? So now let me show this off with one last example. When we look at the molecular orbital diagram for diatomic carbon, it looks something like this. And here's the effect of the mixing right here, that this sigma, you would have expected it to be down here, but it's not down here where the arrow is, it's up here, and then that changes the order of the energy levels. So this is what it looks like for diatomic carbon when you make a molecular orbital diagram. I'm not going to go into the details of it because I've already described all the pieces. Here the bond order is 2, because you add all the bonding electrons together and you subtract the antibonding, and then divide by 2. It's not paramagnetic. All right, last slide, almost there. As a student, I'm guessing you want to know what you're going to need to know, and here it is. So you need to know how to draw this molecular orbital diagram. So for example, you need to be able to draw this. You need to know how to deal with this sp mixing as to whether this sigma 2p or pi 2p is higher in energy, which we just talked about. You need to determine a molecular orbital electron configuration. This is how we ask it on multiple choice things and computer-based homework, because it's easy to do. And basically you can just draw the pretty picture and then say, hey, sigma 2s, I got 2 electrons in here. Sigma 2s star, I got 2 electrons. And you can just count it up, just like we do with atomic electron configuration, so on and so forth. You need to know how to calculate bond order, and then know that a triple bond is stronger than a double bond, which is stronger than a single bond, and and then the trend for length. And then you need to be able to tell paramagnetic and diamagnetic. And so that's what you need to know how to do. And so if you can do all that, you're set. Cool, thank you very much for hanging in there for a long video. Unfortunately, MO is kind of complicated, and you've got to put it all together at once in order to actually do any problems on it. So we have to kind of put it all together. I do have a second video on examples of molecular orbital theory, and I highly recommend you watch that as well. All right, that's all I have in this video. Thanks for watching.